Thank you very much. Yeah, this title kept on evolving, but the contents remains very much the same. So to begin with, let me thank the organizers for inviting me to join this wonderful non-commutative geometry program. And since this meeting is about the interactions, I want to show interactions between non-commutative geometry and Hopf algebras, at least a little bit of it. Okay? So this is based on joint work with Ludwig Dabrowski, who is right here. So if you have any questions, you can ask him immediately, right away. Let me begin by telling you my plan and my goal. So what we wanted to do, we wanted to go in a construction of a non-commutative join from compact quantum groups, which is what we did with Ludwig and others a bit earlier on, to something a bit more general, going to Galois objects. It's using Paulo's language, it would be like going from wheat to sugar, right? So this is. So I wanted to go, say, from Hopf algebras to something a little bit more general, Galois objects. Okay, so let me explain, before giving a formal definition, which of course will appear in my slides, let me give you at least some feeling of what is meant by Galois objects, because these are things that have no good classical meaning. I mean, the only good classical meaning I'm aware of is if you think about an affine space, you know, everybody knows the difference between a vector space and an affine space, but when you look at it topologically, they're just the same thing, right? If you say that you have some space X and that you have a group G acting on it, and if you say that this action is free and transitive, then, well, I mean, of course, this still doesn't have a neutral point, but it's homeomorphic to G. There's nothing new, right? But you go a little bit beyond it and say you take as your X, say, a quantum space, the notorious non-commutative torus, which will again appear in my talk, and then you have an action of a class equal to torus on it, and guess what? The action is both transitive and free. So here I have a Galois object. You have something which is, if you want, like a principal bundle of one point, but this fiber, this unique fiber, is no longer, if you want, homeomorphic to the group acting. So the moment you move beyond classical spaces, this idea of Galois objects becomes very interesting and very potent, but also, being an honest man, I want to say that it's very difficult to nail them down, to see these Galois objects which are not Hopf algebras. And part of my effort is actually to show you that we can produce them, and we have a little factory producing these Galois objects that are non-trivial, okay? But just to give you a feeling that it is really non-trivial, I remember that there was a PhD physicist in France, unfortunately, after so many years, I forgot the name, who did it, just classifying Galois objects of a very famous and simple Hopf algebra of regular functions on SL2C. I mean, that's something very classical. And say to classify all Galois objects of a such Hopf algebra was a PhD thesis, which required a lot of nice machinery. And I'm not at all sure that it's done, say, for SLQ2, I don't know. Okay? So these, and I remember the result was given, these were some algebras which, as far as I could see, they would admit no bounded representations. So it had nothing to do with Q deformations. Yeah. So these are very wild objects. Okay? But Galois objects can be produced from Drinfeld doubles, and I'll show you how to do it. Okay? So what are the applications? Well, so first, as I said, I want to show you how to produce Galois objects from Drinfeld doubles, and they all occurred in our work with on Hopf cyclic homology, where we just realized that stable anti-Drinfeld modules are nothing else but modules over what we call anti-Drinfeld doubles, which are slightly twisted versions of Drinfeld doubles, and they happen to be Galois objects, and I will show you today how to make them into bi-Galois objects and produce non-trivial examples for our main result. So there's some mysterious link with Hopf cyclic theory, which is at this moment completely unexplored, but for the time being, these are very good examples producing, if you want, quantum coverings. Okay? So that's what I'm going to show to you today. But since everybody loves non-commutative torus, let me bring it up again. There is some very interesting recent work of Dabrowski, Hajac, and Zuka, who actually study quantum torus bundles. So the point is to have some non-commutative principal bundles, but who have as fibers, say, a 2 torus or 3 torus, you know, These are the fibers, and having such, or a circle, okay, and having such circle or toric principal bundles, these guys are able to produce nice new Dirac operations and spectral triples. So I hope that sooner or later this will be applied in their work. At least we are just providing this topological background for doing spectral geometry later on, possibly, hopefully. Okay, so these are applications and motivations. Now the plan is very simple. I want to very quickly recall the basics so that we speak the same language. And then what I want to show to you is first I want to explain a little miracle of how it happens that the diagonal coaction of non-commutative Hopf algebras on the braided tensor product of Galois objects is indeed a homomorphism of algebras. And, whoops, I see it on my screen here. I still have like good 4.5 millimeters here. Okay, so anyway, the last line is applied to anti-Drinfeld doubles and quantum tori. So that's the invisible line. Applied to anti-Drinfeld doubles and quantum tori. So, okay, so I want to construct a braided joint comodular algebra of a bi-Galois object. I want to show that this is indeed a principal comodular algebra, which, if you want, is an algebraic lingo of saying that we have a compact quantum principal bundle. And I want to just use it for these two cases mentioned in applications. Okay? Now, okay, it's obvious for topologists, right? So I don't have to spend much time to recall it, but just let me still do it very briefly. What is a joint construction? Well, it's something very simple and very charming. You take two topological spaces, x and y, you take their Cartesian product, you multiply it by unit interval, so you get some nice big box. But the big box would be boring, so what do? You collapse, say, x at your left side and y at your right side, and you get something far more interesting. You can also think about it as having your space x and your space y, and you take all intervals that have one endpoint in x and one endpoint in y. This is how you get a joint construction. Okay? And now, this is, of course, for any topological space, but in particular, you can take, say, compact Cartan principal bundles, and I use this adjective Cartan just to signal that I don't care about local triviality. I don't assume it, okay, which is normally assumed when you utter the words principal bundles. And when you have a join of two compact principal bundles, and then you equip this with a natural diagonal G action, then it's again a Cartan principal bundle, which is basically immediate. Maybe I'll just write the formula so that you see there is no misunderstanding of what I mean by this diagonal action. So what is an element in this join? So this is some equivalence class of a triple, right? I have something in x, I have something in y, and I have my parameter t running the unit interval, right? And then I divide it by an equivalence class. So how do I act on it with an element of G? Well, I don't touch T. What I get is XG, YG, and untouched T, okay? So for this action, this is again a compact Cartan principal bundle. Which is completely obvious, but when you go quantum, this is our main result, actually. Okay? But for us, it's even there's a certain struggle to say what we mean by having such an action. This is like a pre-result for our main theorem. And again, my apologies to topologists who know it by heart, but let me very, very quickly tell you some examples. If you, for instance, in particular, everybody agrees that G itself is a principal bundle, so you can just take a join of G with itself, okay? And if you take the simplest non-trivial case, Z2, well, then what you get is S1 over RP1. When you take G to be the circle, then you get the Hopf vibration S3 over S2. And finally, when you take G, say, I mean, not finally, can go on, but say that's enough. If you take G to be SU2, well, then what you get is the instanton vibration, S7 over S4. So for me, when I first realized it, it was very nice and amazing because all these beautiful vibrations you remember from school are just examples of a very general construction. And I find it quite fascinating. But you can go on. Also, well, we managed to go on to the quantum case, and here I cannot resist the pleasure of mentioning Arbeitsdiploma of Markus Pflaum, who, without actually realizing it, did it for SQ2. So there was no join in his Arbeitsdiploma, no definitions like this, but the very construction which exists and which we recently proved with Ludwig and others using index calculation, indeed gives you non-trivializable compact quantum principal bundle, was actually initially constructed by Marcus for his master thesis, which I find quite impressive. So that's what we can do here. Maybe one more thing I want to mention is that in the classical case, this is a very simple exercise to prove that such a bundle is trivializable if and only if G is homotopically is homotopic to a point, which never happens for compact groups except for the point itself. So this means that whenever you take a compact group, you are always bound to get a non-trivializable bundle here. And we very much would like to prove the same for quantum groups, but this is still an open problem. We managed to prove it for SUQ2. Now I'm going to insult your intelligence by showing you the braids. I guess that at the meeting of non-commutative geometry, you all know it by heart, but I still couldn't resist the temptation because this picture is so beautiful. But I guess all of us, we have all the neurons braided after so many years of work in non-commutative geometry, so let me skip the definition and tell you what I mean by braidings of algebras. But before I do so, let me mention some very general concept, which is very straightforward and very easy. Namely, what is a factorization of two algebras? So imagine I have, my algebras are unital. Okay, I assume that everything here is unital. So I have two unital algebras over some ground field, say A and A prime. I have a pointer. Okay, A and A prime. And I take this vector space, A prime tensor A and A tensor A prime, and I consider a linear map sigma between these two vector spaces that has the following properties. So first, I wanted to preserve the units. So if I take one tensor any element in A, then as a result I must get one on the other side. So left one is in A and right one is in A prime. I don't distinguish them. So that must happen for A, and this must happen for A prime. So if you want one is just flipped into one. Next, what I want is that this kind of generalized flip preserves both multiplication m prime and preserves both multiplication m in the sense that I wrote here in these two equations, right? Here I use this length numbering. This equation what happens, you really have to unravel the spaces. So here I have m prime, so it means that the first equation happens on A prime tensor A, and the second equation happens on A prime tensor A. Okay? And I'm just using the usual leg numbering notation. So when I have sigma 1, 2, I flip just the first two legs and I don't touch the third one. Similarly to 3 and 1, 2. This is just an abbreviation in order to skip writing identities. Okay? So here, of course, m and m prime just mean appropriate multiplication maps in A and A prime respectively. Okay? So when we have such two properties satisfied by a linear map sigma, then we call it the factorization, and you will see in a second why it's important. But we can request a little bit more. For instance, we can consider what happens when A prime equals to A. It doesn't have to, but I don't want to go into braided categories. I just want to have one algebra. So then I can use this length numbering notations quite freely. I can mix many legs because when A prime is equal to A, I just have this triple A tensor product. And I can demand that the braid equation be satisfied. Well, so when I have a factorization that on the top of it satisfies a braid equation, guess what? I call it a braiding. Okay? And this is what, again, wow, so I have to write it on the blackboard because this equation is important and it's completely vanished here. Okay, so why are factorizations such a big deal? Well, because they actually classify all possible associative algebra structures on a vector space A tensor A prime, such that both A tensor 1 and 1 tensor A prime are subalgebras of A tensor A prime. Okay, so whenever it happens, it means that you must have a certain general flip sigma that has these two properties. And of course, the multiplication, which is not visible, so let me write it. This multiplication in for this new algebra structure is the following. So I have A multiplication in A tensor prime, which is simply given in the following way. So it goes, of course, from A tensor A prime, tensor A prime. It must land in A tensor A prime. But in order to achieve it, well, first, and I want to use multiplication in A, and I want to use multiplication in A prime, well, what I have to do first, I have to flip the legs of A prime and A. And this is what I'm doing with the help of sigma. So apply identity, sigma, tensor identity. And this way I go into A, tensor A prime, tensor A prime. And now, of course, what I do, I just apply multiplication in A tensors with multiplication in M prime. So that's the missing formula, okay? And whenever you have any algebra structure on the vector space A tensor A prime that has this, these two properties, that A tensor 1 and 1 tensor A prime are included as subalgebras, then what always stands behind is this sigma. I mean, it's not a very deep observation, but I find it something very useful.
So the idea is
Sorry? What? I don't hear. Oh, yes, of course. No, of course. But I said that everything is unital, of course. Yes, of course. Surely, yes. Yeah. And, But now I want to ask a question to which I don't know if there is already an answer. It shouldn't be horribly difficult to answer this question, but I'm not sure if anybody considered it so far. Okay? So we can now ask the following question. Imagine that I have more structure. Imagine that my algebras are not only algebras, but they're actually comodular algebras. So what I have a coaction on A. So I have a map from A to A tensor H, okay, which is an algebra homomorphism. And I also have a map from A prime to A prime tensor H. And I use Sweedling notation to denote these maps. So I'm mapping A to A0 tensor A1, summation suppressed and assumed. And I map A prime to A prime 0 tensor A prime 1. Okay? And I have a factorization, okay? So I have this linear map from A prime tensor A into A tensor A prime, so it satisfies the two aforementioned properties. And what I want this sigma to have one additional property, namely, I want to have it the property that if I take this sigma determined algebra structure on A tensor A prime, I want the usual diagonal coaction, and by diagonal here I just mean given by this formula, okay? I want it to be an algebra homomorphism with respect to this sigma determined algebra structure, okay? And we have some answers to this question. I mean, we give examples. So, for instance, in our case, what I'm going to tell you about, I'm going to tell you how to use a H-Galois structure to produce actually more than just factorization, to produce a braiding that would do it. There's a beautiful paper by Richard Ness and Christian Vogt who do the following. They take A to be a comodular algebra. I mean, they do it all for locally compact quantum groups. They use multiplicative unitaries in the analytical setting. But the algebraic backbone is the following. So we have A as a comodular algebra, but when we have A prime as a comodular algebra over the Drinfeld double. So it is also a comodular algebra over H, but actually also has a little bit more structure. And with a little bit more structure allows you to define the braiding on A tensor A prime such that the diagonal coaction is indeed an algebra homomorphism. So we have these different possibilities with having some extra input datum to actually construct such sigmas that this property holds. But maybe there is some nice universal solution. Maybe it's easy to characterize such sigmas. I don't know. It just occurred to me after Richard's question at our meeting in Warsaw in August. Okay? So, as I said, I don't know if it already has been answered. I don't know if anybody thought about it, but it should have not that too difficult solution. Okay? Now, let's go on. Now, let me just introduce notation. This is notation from Hopf-Galois theory. I will have to use both left and right structures. As you can see, everything is here in doubles. I have everything which is left has its right version. So maybe in order to avoid confusion, I'll just say focus on left and right is completely analogous. So I have some, say, left comodular algebra, and I define coaction invariant subalgebra. So this means all elements in my comodular algebra on whose coaction is trivial in the sense that it produces one tensor something on which you coact. If you want to think about it geometrically, you can think about P as functions on some totals on some G space, and then what you have here are just functions invariant along the orbits of the action of G. So if you want functions on the quotient space. Okay? And now here comes a key condition. So when do you call such a coaction, respectively left and right, Galois coaction, and the whole thing H-Galois extension, I mean the extension of this algebra, subalgebra B to the big algebra P? Well, you call it when the following map is bijective. So what you do here is you take, in the left version, take the right leg of this balanced tensor product P tensor over BP. Okay. So here I use notation. I use the same letter B for left coaction invariance and right coaction invariance. A priori, they have nothing to do with each other. Right? I see absolutely no condition yet, no compatibility between left and right coaction. So in fact, I should use here maybe B left and here B right, but that's just a slight abuse of notation. And in a second, actually, they will coincide. So probably that's why I did it. Okay. So what I do, I take the right leg of this balanced tensor product. I apply the left coaction. And so this gives me x minus 1, which is in the Hopf algebra, and x0, which is in my comodular algebra P. And then I multiply it with an element which stands on the right. So I multiply it with this y here. Okay? And now I demand that this map be an isomorphism. Okay? And if it is, I call it H-Galois, and analogous case, analogously the right case. Maybe just a quick reminder for the very few of you who might not know it is that the classical meaning of this map is actually very simple, because what you have here is just, if you want a pullback of a map which goes from x cross G to x cross x, and is given by the formula. I'm doing the right case. X comma G is mapped into x comma xg, and of course this is a pair of points in the same fiber, so you can consider the image just in the fiber product over the quotient space. Not the full Cartesian product, but there's the fiber product of x with x over the quotient space x mod g. So if you dualize it, translate it into algebra, you'll get exactly these maps in both right and left flavors. So if you want, this is an algebraic version of the freeness condition. And if you're an algebraic geometer, you know that this is the way you handle principal boundaries in algebraic geometry. And because if you are interested why it's called Galois, well, that's because if you have a finite field extension, say B and P are fields, and the dimension of P over B is finite, then in fact the Galois property is also encoded by this map, where H is just the Hopf algebra of functions on a finite Galois group. Okay? But it's an exercise to prove it, not a trivial one, but an exercise. Okay, now let me go to something more modern, something which appeared in a paper of Đurđević, who made the following beautiful observation. So I'm going to use, he did it all in the right-sided version, but I'm going to need it in the left-sided version. Doesn't matter, it's completely analogous. He observed the following phenomena, that if you have, say, this left H-Galois extension on B, then the following map, which is written for you here explicitly, is in fact a braiding. Well, at this moment you can protest, because I told you I'll notice a braiding for algebras, for tensor products over the field, but it doesn't matter. The braid equation, you can write it down. You can assume that this is a B bimodule map, and you can write it down even if it's tensor product over something more general, so there's absolutely not a big deal about it. Okay? And he wrote this formula, and then he proved that it actually it satisfies the braid equation, and is also a factorization. So you really have a braiding when you look at it. And okay, it's not extremely difficult to prove it and do it, but it's definitely non-trivial. It definitely requires some sweat to check that all these braid equations hold and are satisfied. And instead of explaining this to you in detail, let me give you special cases. So first special case is something which I intend to handle. This is what my talk is devoted to. Namely the case when this fixed point subalgebra, this coaction invariant subalgebra is just the ground field. So this is when I have a left Galois object. Okay? So that's the case which we are going to explore. This is where we're going to use this braiding. And, well, you can go into even more special case. Well, now the only thing which is missing is explanation that S is the antipode of H. So that's the only line which is gone, is S is the antipode of the Hopf algebra H. So if you go even further to even more special case, and now we assume that this Galois object is in fact the Hopf algebra itself. Of course, every Hopf algebra. Did I define the Galois object? My goodness, I gave you a feeling, but did I define it? Okay, so if you want, it's defined over here. But it's very important to stress it. So I say that P is an H-Galois object if and only this is an H-Galois extension of a ground field. So in other words, you have this H-Galois extension, and now we assume that your fixed point subalgebra is just trivial. So that's geometrically speaking saying that, okay, you have a freeness condition, so you have a free action of G on X, but also you say that the action is transitive. You have only one orbit. Okay, so this is this interlude I had at the beginning about having non-trivial bundles over one point. Okay, so but of course, a group itself is a principal bundle over one point, and this is the case here when you can take just a Hopf algebra as a Galois object. And then what you realize that this, when you look at this formula, what it gives you is the celebrated anti-Drinfeld braiding. So it's something very well known and very much used. Okay, and you should also observe that in case when, and this is a very crucial point, in case that P is a commutative algebra, okay, in case when P is a commutative algebra, this braiding is just a flip, okay, which is immediate because then you can pull out X outside of Y, and then what you have here is just, you have Ken inverse applied to Ken or the other way around. So this will give you nothing else but one tensor, Y tensor 1. So this will be nothing but a flip. You'll map X tensor Y to Y tensor X, and of course now you don't have to worry about having a flip over B, because if P is commutative, then its subalgebra is also commutative. So you are good. Okay. But I will show you an example that if in case your Hopf algebra is commutative, this still might be non-commutative. That's actually what happens for quantum torus. Yeah, I should have stressed that in this business with factorization, okay, over here, the obvious solution to these properties is just the usual flip. And we take the usual flip, as you can expect, what you get is the good friend tensor algebra. Okay? Sorry, I should have somehow mentioned it. Good. Now, we go to these left Galois objects, and we have a Jurjevich braiding for Galois objects. So this gives us a new algebra structure. And to somehow distinguish it from the usual tensor algebra structure, I use this underlined notation. So I underline the tensor product. So as a vector space, the red and the black are just the same. But when you look at the algebra structure, these are two completely different algebras. Okay? And the second one, the red one, I call the braided tensor product algebra, where I assume that A is a left Galois object. Okay, so here you have a key lemma. I think Paolo also had a key lemma. Yeah? He also had a key lemma. So, okay, the key lemma says the following, that if we use this left Jurjevich braiding, and then we write down the formula for the right diagonal coaction, then in fact for this braiding, this right diagonal coaction is an algebra homomorphism. And when you just look at it like this, we just computed it and it checked out. This was somehow miraculous, but in fact it's something absolutely obvious if you think about it. Well, what happens is the following, and this is a very powerful mechanism which is used over and over again. Namely, I take my A, and at this level, in fact, I stated it here just for Galois objects because that's all that I need for this talk. But for what I'm going to show you, we can go further. There's no need to assume that this is a Galois object. Okay, let's stick to it. So I have this map. This is A is a left Galois object. I have a map which goes from A tensor A to H tensor A. All right? And here I can take the usual tensor algebra structure, and I can apply the following right coaction, which is an algebra homomorphism. I can take identity tensor right coaction on A. Of course, this is an algebra homomorphism, and it goes to H, tensor over A, tensor H. Okay? And now what we do is the following. Since this is by assumption, by this Galois property, this is an isomorphism, what I can do, I can pull this tensor algebra structure from H tensor A to A tensor A. And this will be exactly the braiding. This will be exactly this braided tensor product algebra. And the only thing you actually have to verify is that when you pull this coaction via the canonical map, what you get is exactly on the nose the diagonal map. And that's it, you are done. And obviously, it's an algebra homomorphism, you don't have to do any calculations. The only thing you have to observe is that indeed the thing that actually gives you this new algebra structure pulls something which is an algebra homomorphism to what you want to be an algebra homomorphism. Okay? So that's no longer such a miracle, if you think about it. And I guess that this is one of these mechanisms you use very frequently. Okay? Now, I can, now that we are done with the diagonal action, because I guess I don't have to mention it at a non-commutative geometry meeting that if your Hopf algebra is non-commutative, the diagonal action is not an algebra homomorphism, if you would use the usual tensor product structure, right? If I wouldn't do the braiding here and I would multiply here non-commutative algebra, well, then there's just no chance that it's an algebra homomorphism. I have to do something to make it an algebra homomorphism. Okay, so now how do we do this joint construction in the non-commutative case? Well, so first we construct our box. So you think about it as x cross x, and you think about it as cross the unit integral, right? So this is my box. I just have, say, all complex valid continuous functions of unit interval, and I take the usual tensor product with a braided tensor product of A with itself, okay? But now this would be this boring part. This would be the box, and all I want to have a joint. So in the classical case, I got my joint from the box by appropriate collapsing, taking equivalence relation. So here at the algebraic level, it will mean that I'll have to carve out in this too big algebra. I'll have to carve out the subalgebra. Okay. So how do I do it? Well, I use evaluation maps. I can apply identity here and evaluate at 0. I have some function here. I evaluate at 0, and then in general, I would land in this braided tensor product, but I demand that in fact when I evaluate at 0, I land in the particular subalgebra, which is just complex numbers tensor A. Okay? And on the right-hand side, completely analogously, I demand that when I take my evaluation, so evaluation at 1, I will land not just anywhere in A tensor A, but I will land in A tensor C, which is a particular subalgebra. So when you choose, when you define your subalgebra like this, that's what we call this H-braided joint algebra. And of course, this is, you can very easily verify that if everything here is commutative, and if you complete everything to the sister level, this will be exactly the picture you have of a classical joint, okay? At least for these compact Hausdorff spaces. All right, so that's, if you want, the main hero. This now explains what I mean by the braided joint. So braided refers to just this algebra structure, which is not relevant for that definition. I will need it later on to turn this joint algebra into joint commodule algebra. And this is the way you get, if you want, a non-commutative version of a joint construction. Now, well, it's about time for the main theorem, but before the main theorem, let me tell you an obvious lemma. Well, the lemma says that now, if I take the obvious coaction on this boring too big box algebra, which is identity on functions of unit interval, and the diagonal coaction on the braided joint, which by now we know this is a good commodule algebra coaction, okay, then in fact this coaction restricts and co-restricts to the joint subalgebra. On the algebraic level, it's a complete triviality. But one of the reasons why I mention it is because the moment you do it for sister algebras, which is what we did with Kennedy Kommer and Elmar Wagner and Ludwig, in fact, it's a bit tricky to do it on the sister level, but yes, it's doable, it works when your tensor products are minimal, but then it's no longer obvious when your sums are no longer finite. Okay? But here they are. And it's a trivial exercise to prove it. And once we prove it, we are ready to go to the main theorem, which again has, here, luckily you can still read the last line, okay. Which says the following. So when now let's focus on the assumptions we have. So now, not only I assume that, this was actually already needed here. I somehow skipped telling you the assumptions. Okay, so in order to have a coaction, I need to have a bit more. I want to have that this A is a bicomodular algebra over H, which means that these left and right coactions commute. So they are still completely independent input datum. Left and the coaction does not induce right, and right does not induce left. They are totally independent, but I assume that they commute. So this means that if I first go from A to A0 tensor A1 by the right coaction, so this is, say, using right coaction, and now I want to go down by taking the left coaction tensor identity, then I apply the same thing as if I went the other way around. Yeah, which is going first down by the left, so A minus 1 tensor A0, and then going right by the right. Okay, so these two coactions have to commute, and I assume that for the left coaction A is a Galois object. Okay, and this is, I suppose, yeah, this is. I'm sorry, I was speaking a bit too fast. I didn't read the assumptions for you. This is what was already needed for the key lemma, of course. And so that you have this structure, but now the extra thing that I assume is to get the main theorem, and this is I suppose spelled out over here is that well, there is a small technical assumption that the antipode of H is bijective, but that's very minor. You never meet in real life a Hopf algebra that has an antipode that is not bijective, but it does not follow from the axioms of the Hopf algebra, so you have to assume it manually. But now that's the crucial part, that now we assume in addition for this theorem to work. So we assume that this right coaction, which commutes from the left coaction, which is Galois, but this right coaction is also Galois. Okay? And here we have a certain conflict of terminology, because there is so-called theory of bi-Galois objects due to Schauenburg, but that's why I somehow refrained from using this terminology. But in his case, it's more like a transfer, because what he has a right coaction, which is Galois, and out of it he constructs a new Hopf algebra which acts on the left, and this left coaction is also Galois, but his input datum is only one. I mean, he has only one coaction, and then out of this he produces another one. What we have here, we have two really completely independent coactions that happen to commute with each other. Okay? So that's what I would call bi-Galois. But anyway, whatever you call it, it still remains the case that I'm having two commuting coactions left and right, and both of them are Galois. Okay? And once I have it, and then I have my construction of this joint comodular algebra, the main result is that it is principal in the sense that the canonical map, this Galois map, it induces. Remember this map? Maybe I will flash it back. Yeah, this one. So first, we for P being the join, okay, we can prove that this map is actually bijective, which requires some technology. This is the main part. This is the main result. And we also prove that this is H equivalently projective. So, and that's the meaning of principality. I say that I have a comodular algebra basically when I have bijective antipode, when I have a canonical map bijective, and when I have equivalent projectivity. Let me explain this equivalent projectivity, because it's a very simple concept. Well, imagine that I have an M, which is, say, a left module over some algebra B and a right comodule over some coalgebra C. And then I take the multiplication map from B tensor M to M. And as everybody knows, this module is projective if and only if this multiplication map splits as a left bilinear map. Okay? So in order to make it equivalently projective, I demand a bit more. I demand that the splitting S of a multiplication map not only is left bilinear, but is also right C collinear. Okay? So there is an equivalent splitting. And so, of course, that's a slightly stronger condition, right? Everything which is equivalently projective is necessarily projective, but not the other way around. It should not be confused with relative projectivity, which is a completely different animal. Okay? So we prove that indeed this coaction which restricts and co-restricts to our join algebra, our braided join algebra, that indeed this coaction has these two properties, so it deserves being called principal. If you want, what we get is an algebraic version of a compact principal bundle. And moreover, you can also prove that this fixed point subalgebra that you have is something which maybe is not immediately to be expected. I mean, it's not very, if you think about it, you realize that this is what it should be, but at the beginning it was a slight surprise to us, namely that this somehow, this going from Hopf algebra to a Galois of a Hopf algebra is not felt at all at the level of fixed point subalgebra. The fixed point subalgebra will always be nothing else but the non-reduced suspension of the Hopf algebra H. Okay? Yeah, I have 10 minutes, so I still can do examples, but maybe I will define this non-reduced suspension for you, because I think it's very easy to do, and then it's more concrete. I mean, you can do it for any algebra. I take say functions on my unit interval. I take my algebra A. In this case, it will be this Hopf algebra H, so why not do it like this? But I don't take everything. I take only these elements here. Let me denote them by X that have the property that if I evaluate at 0, so it's evaluation at 0 tensor identity of X, I will land in some multiple of the unit, and the same at the other endpoint. So evaluation at 0 and evaluation at 1 will always be nothing but a number. Okay, so if you want the fixed point subalgebra here, so I can even denote it like this. I can write it A, braided, H braided join with A, and I can write this coaction of H. So this fixed point subalgebra will be exactly the non-reduced suspension of H, which is not a big surprise, because if you look at the join of a group G with itself, okay, and well, if you look at what it is, so what you have is unit interval over internal point of the unit interval. You have just G cross G, but it's collapsed to one copy of G at this point and to another copy of G at that point. So now when you divide it by the diagonal action of G, what will happen? So here you have just a point as your space. Here again you have a point as your space, and when you divide G cross G by G, you will have basically G. So this is exactly the non-reduced suspension of G. Okay. So we have the same phenomenon, but what is very nice is and was a little bit unexpected to begin with, is that in fact it's always just an H. I mean, whatever Galois object we take, and we can have plenty of different non-trivial Galois objects A over H, this fixed point subalgebra will always come out the same. Okay? So now let's do some examples. The promised quantum torus. I'm doing it completely algebraically, but I have very little doubt that you can do everything. We have a star structure defined and worked out. There should be absolutely no problem with doing it on the C-star level or some smoother level, whatever you want to work with. Okay. So, but I'm doing it completely algebraically over here. Okay. So I take as my Galois object this say irrational rotation algebra, but I just take polynomials. I have two unitaries that commute modular phase. Then well, in the joint construction, I take, and it's in an obvious way, Galois object of the Hopf algebra of a classical torus, and the coaction just couldn't be simpler. If U is generating unitary of this non-commutative algebra, and capital U and lowercase u is generating unitary of the Hopf algebra of functions on the two torus, then the coaction sends U to capital U to capital U tensor lowercase u, capital V to capital V tensor lowercase v, and the same on the left. So that's so simple that I guess it's a waste of time to explain it any further. And now you can of course have your generating unitaries on the left or on the right of your tensor product, right? Remember, we take this braided tensor product with A over itself. Well, you crank this machinery, you try to see and compute what it is, and you do have some nice commutation relations between these generators, and very easily see, for instance, using the diamond lemma, I can very easily see that powers of these guys will produce you a linear basis. And then when you try to unravel explicitly what you mean by this joint algebra, well, you'll have things given by generators. These guys generate this braided tensor product algebra, and you have some coefficients being functions on the unit interval, and they have to have some vanishing properties for appropriate indices. Okay, so you have some very particular algebra inside here. But what at least excites me about it is that this is a theta deformation of some non-trivial torus bundle. Okay. So if you just take the classical join of two torus, well, you get the T2 principal bundle, which is obviously non-trivial. Okay? And now we have the same thing, but now what happens is that our fiber is classical, our base space is classical, but our total space is very much theta twisted. Okay? And here just one observation why we were not happy with this example, and we explored it a bit further. Well, because you can say here, forget it all at the braiding, because this is a commutative Hopf algebra. Diagonal coaction is well defined. I don't need to do anything. I can still do this braid construction and everything works. Yes, it's true, it does. But then this algebra that you get over here is, if you want, slightly less interesting. Now, we get, even though we have a Hopf algebra which is commutative, the braiding which it produces via the Jurjevic formula is still not a flip. And that's because this Galois object here we take is non-commutative. Okay, so I hope that this will be a nice playground for Ludwig and Andrzej and others to do spectral triples on. Okay, now there is a saying, a man does not live by quantum torus alone, so let me give you some other examples, and not a semi-simple example. This is, if you want, not interesting from the point of view that this is not any fancy Galois object, this is just a Hopf algebra H, but this is a finite-dimensional Hopf algebra. You take it at some root of unity. This is definitely not cosemi-simple. It has one beautiful feature which I want to stress: S squared is not equal to identity. Okay, that's very important for us. This is what makes a distinction between Drinfeld doubles and anti-Drinfeld doubles. And again, you can just crank the machinery and compute what it really is. And the way you should think about it is that this is some finite quantum covering, which encapsulates a very simple classical covering, because if you look at this Hopf algebra, if you look at the characters for this algebra, if you want, in other terms, if you look at the classical subgroup of this finite quantum group, then it's of course just Z3, yeah? Just have 3 roots of unity. And when you take the join of 3 points with 3 points, well, you'll get some nice classical covering. You have a bunch of lines, and all of this is some kind of quantum encapsulating of this classical covering, which again has all the feature of a covering. So because you get a compact quantum principal bundle from our main theorem. All right, but this we didn't like, because the other one we didn't like because Hopf algebra was commutative, so we could forget the braiding. This one you don't like because this could be handled by our previous result for Hopf algebras and compact quantum groups. So we wanted to have some genuine non-trivial Galois, actually bi-Galois objects coming into the game. So since it's already not so trivial to get Galois objects, how about bi-Galois objects? But then I recalled that some time ago we wrote a paper about Hopf cyclic homology. And then we already had we had certain commodule algebras that were Galois objects, but they were Galois objects only on one side, okay? And now we need this bi-Galois structures. How do we get it? But first let me define it. So I take the usual Drinfeld double algebra. So I take a finite-dimensional Hopf algebra. I take the tensor product of a linear dual of this Hopf algebra and the Hopf algebra itself. And now if you ignore this red S squared, the formula that I wrote for you here is just the standard formula defining your multiplicative structure for the Drinfeld double Hopf algebra. And the way, this, for instance, this is the way you get the Drinfeld modules, right? So Drinfeld modules are modules over such an algebra. And now what we needed to see, well, our anti-Drinfeld modules also modules over some similar algebra, and the answer was yes, but the only thing we had to do was to stick in this S squared. into the formula and have the fast twisted algebra structure. So that's why it's important for us that this S squared is not identity. Okay? But now this is what was done 10 years ago. And now we wanted to produce also a right coaction, also a left coaction, which would commute with the right and which would be also Galois. Okay? So how did we do it? So I repeat, from the previous stuff, we already knew, okay, that if I take simply the coproduct on my Drinfeld double Hopf algebra and I view it as a coaction on this anti-Drinfeld double algebra, then it is an algebra homomorphism and it has this Galois property. So this is a right Galois object, no problem. For the usual coproduct. So I use this coproduct and it turns out to give me a comodular algebra structure for this new for A of H. Okay? So now we want to construct a left coaction which would have, I repeat, these properties. First and foremost, it would be an algebra homomorphism and it would commute with the right coaction and would again be Galois. And by some playing around with examples, we realized again all that we need to do is to stick in S squared into the formula for left coaction. And the moment we put it in, all the assumptions of our main theorem are satisfied. Yes, we have a bi-Galois object, and for every such a bi-Galois object, we can construct this braided joint comodular algebra. And I think that this is a point at which I want to stop. I have just one more quick thing to tell you, a slight advertisement, if I may, since this is a big forum. We have at my institute at IMPAN, we have many postdoctoral programs, but some of them are aided by the European Commission. And we have such a program, it's called Impact. I run it together with Andrzej Sitasz. And basically, we hire every 2 years, we hire 2 postdoctoral fellows for about 2 years. So if anybody is interested, I strongly encourage you to Google it up and apply it if you feel like it. Our winners so far are Liviana Parmesano, una brava ragazza italiana, and a guy from the Czech Republic. So as you see, IMPAN is an equal opportunity employer. We have perfect gender balance. Thank you very much. Oh yes, thank you so much. This was a question just supposed to be asked by Nigel Hickson, but yeah, sorry, yes. In fact, Nigel was one of the first victims of my talk on this subject. And of course, his question was, well, how about iterating the procedure? Everybody knows, at least all topologists know, that one of the reasons for Milnor to inventing the join was to iterate it to get a classifying space, right? You take it infinitely many times to have a classifying space for G bundles. So of course, now we want to know if we can do it over here. And the answer is yes. We just checked it and we can do it in the following way. And this is also interesting from the point of view of cyclic homology, because it's the same trick which was used by Hara and Stefan to transfer relative cyclic homology to Hopf cyclic homology. So what you do, you just, I use this canonical map once, but you can iterate it. I just told you, okay, so in order to do the braiding, I just use this isomorphism, which goes from A tensor A, all right, to H tensor A. But I can take this as many times as I want. So I can take nth tensor power of A, okay? And I can go step by step. First, I apply the canonical map to first 2 copies. So I get one H clicking in, then to another 2 copies, and at the end of the day, I will end up with some big tensor power of H and just one left alone A, okay? And this is what I can do to have, if you want, a multi-braiding of multi-tensor product, and the same works. Just a bit more difficult to prove because you have to use some induction step, but it's not a big deal. So we can do it. And this was exactly, if you want, this map which was used by Hara and Stefan to transport relative cyclic homology to Hopf cyclic. Thank you, Ludwig. It's very good to have your collaborators at your talk.